This is problem 837. In this problem, you have a thick-walled stainless steel pipe of inside and outside diameters of 20 millimeters and 40 millimeters respectively. This pipe is heated electrically to provide a uniform heat generation rate of 10 to the 6th watts per cubic meter. The outer surface of the pipe is insulated while water flows through the pipe at a rate of 0.1 kilograms per second. So we'll draw a schematic here of our pipe. The pipe has a length L and an inner diameter DI, outer diameter DO, and we know we have water going into it at M dot. And if you look at part A, the water inlet temperature is provided, and we know the water mean outlet temperature. Let's first look at what is given. We're given that D sub I is 0.2 meters, D sub O is 0.04 meters, Q dot is 10 to the 6 watts per cubic meters, M dot is 0.1 kilograms per second, and for part A, we know that TMI is 20 degrees C, and T sub M comma O is 40 degrees C. So we're trying to find then the required pipe length. Now to do this, we need to determine what the properties are of the fluid both inside the pipe as well as the pipe wall itself. We know the pipe wall is comprised of the stainless steel AISI 316. So for the stainless steel pipe wall, we're looking at in table A1 material properties for AISI 316. The only property we care about with the steel is the thermal conductivity K, which is this column here, which corresponds to 13.4 watts per meter Kelvin. So if we go back to our diagram here, we say K is equal to 13.4 watts per meter Kelvin. With the water, we want to be able to find a few more properties. Table A6 allows us to determine the properties of saturated water. The ones we care about here are the specific heat for the liquid phase, which is shown here. It's 4.179 kilojoules per kilogram Kelvin. And we'll take the properties at 300 Kelvin, although technically they could be at a different temperature. We care about the viscosity of the fluid, which is 855 times 10 to the minus 6 Newton second per meter squared, or Pascal seconds. The thermal conductivity, which is 0.613 watts per meter Kelvin. And the Prandtl number, which is 5.83. So returning to our document here, we put in then the thermal conductivity of the fluid, 0.613 watts per meter Kelvin. The heat capacity of the fluid is 4,179 joules per kilogram Kelvin. The dynamic viscosity of the fluid is 855 times 10 to the minus 6 Pascal seconds. And the Prandtl number of the fluid is 5.83. So again, the thermal conductivity K here is for the steel, whereas the remaining properties are for the water. So now we can get started. Let's first write an energy balance on the entire pipe wall. So what we'll do is we'll draw our control volume around the entire pipe, and we'll reproduce it down below. We know the outer walls are insulated, so we're not going to have any heat coming in or out on the outer walls. So really all we have is we have an E dot in coming in and an E dot out going out that pertain to the water. And we also have an E dot gen inside that relate to the heat generation of the pipe wall. So if we write out our first law, dEc v dt is equal to E dot in minus E dot out plus E dot gen. We know everything's at steady state, so this goes away. And we know that what's E dot in is going to be the thermal energy associated with the fluid coming in, which will be m dot c sub p ti. What's going out is m dot c sub p to. And then E dot gen will be q dot times the volume, which will be pi over 4 dO squared minus di squared times L. This allows us then to calculate out what L is. So we say 0 is equal to m dot c sub p times ti minus to plus q dot pi over 4 dO squared minus di squared times L. And therefore, L is equal to m dot times c sub p times to minus ti all over pi times q dot times dO squared minus di squared. I'll move the 4 up to the numerator. Plugging in numbers, in L is equal to 4 times 0.1 kilograms per second times the heat capacity of water, which will be 4,179 joules per kilogram Kelvin, times TO, which is 40 degrees C, minus TI, which is 20 degrees C, all divided by pi times 10 to the 6 watts per cubic meter, times dO squared, which is 0.04 meters quantity squared, minus 0.02 meters quantity squared. Do the math here and you end up with 8.87 meters. So in part B, it is asking what are the location and the value of the maximum pipe temperature. In order to determine the location of the maximum temperature inside the pipe, we need to apply then our heat equation. 1 over alpha, the temperature d time, is 1 over r, d over dr, r dt dr, plus d squared t dz squared, plus q dot over k. You notice that we're using cylindrical coordinates because it matches the pipe wall. We're going to assume that we're at steady state, so that gets rid of that term. We're also going to assume that temperature is only a function of radius r, even though we know that in reality it's a function of z as well, or length or position in the pipe. But we're going to assume that it's only a mild function of z. It's mainly a function of r. So we'll get rid of that term as well. So what we can do then is we can turn these partial derivatives for dt, dr into full derivatives. So we get 1 over r, d over dr, r dt dr, plus q dot over k. All this equals to 0. So to solve this, what we'll do is we'll first move the q dot over k over to the other side. So 1 over r, d over dr, r dt dr is equal to minus q dot over k. Then we'll multiply both sides by r, and this gives us d over dr, r dt dr is equal to minus q dot r over k. We'll then integrate this entire equation with respect to r. This gives us now r dt dr is equal to minus q dot r squared over 2k plus c1. Then we'll take this equation and divide through by r. So it's dt dr is equal to minus q dot r over 2k plus c1 over r. And finally, we're going to integrate this equation with respect to r. And this gives us our general form of the equation. T as a function of r is equal to minus q dot r squared over 4k plus c1 times the natural log of r plus c2. And we need to come up with some boundary conditions for this. The first boundary condition is easy. We know that at the outer radius of the pipe wall it's insulated. So we could say that the first boundary condition is dt dr evaluated at r O, or the outer radius, is equal to 0 as an adiabatic conditions. So the other boundary condition, of course, would be at R equals R sub I. And this would be a convective boundary condition. What this tells us is that the heat flux by convection, which would be H times T infinity minus T at Ri, is equal then to the conductive heat flux, which would be minus K times dTdr at Ri. So first we'll apply our adiabatic boundary condition. We'll say dTdr at R0 is equal to 0, and dTdr at R0 is minus Q dot times R0 over 2K plus C1 over R0. So this means then that C1 is equal to Q dot R0 squared over 2K, and therefore our general equation, T as a function of R, is minus Q dot R squared over 4K plus Q dot R0 squared over 2K natural log of R plus C2. Next we can apply our convective boundary condition. This states that H times T infinity minus T evaluated at R sub I is minus K dt dr evaluated at R sub I. So plugging in our general equation, we get T infinity plus Q dot Ri squared over 4K minus Q dot Ro squared over 2K natural log of Ri minus C2 is equal to minus K times minus Q dot Ri over 2K plus Q dot Ro squared over 2K times R sub I. And we can take this right-hand side and further expand it out as Q dot Ri over 2 minus Q dot Ro squared over 2Ri, or Q dot Ri over 2 times 1 minus Ro over Ri quantity squared. If we bring our H over to the right side, it becomes T infinity plus Q dot Ri squared over 4K minus Q dot Ro squared over 2K natural log of Ri minus C2 is equal to Q dot Ri over 2H times 1 minus Ro over Ri quantity squared. Therefore, we can solve for C2. It's going to equal T infinity plus Q dot Ri squared over 4K minus Q dot Ro squared over 2K natural log Ri minus Q dot Ri over 2H times 1 minus Ro over Ri quantity squared. If we plug it back into our regular expression here, T as a function of R is minus Q dot R squared over 4K plus Q dot Ro squared for 2K natural log of R over Ri plus Q dot Ri squared over 4K plus T infinity minus Q dot Ri over 2H as 1 minus Ro over Ri quantity squared. So now that we have our general expression, we can find then at what radius we'd have the maximum temperature for any point along the pipe. So to do this, let's first take the derivative dt dr and set it equal to 0. We already know that this should occur at the outer radius Ro, but we'll double check here to make sure. So this is minus Q dot times R over 2K plus Q dot Ro squared over 2K times R. This means then that Q dot R squared over 2K is equal to Q dot Ro squared over 2k. So sure enough, this occurs at r equals r0. We need to determine, however, does this point represent a maximum or a minimum? So let's take the second derivative. d squared t dr squared at RO. And we take this second derivative, we get minus q dot over 2k plus minus q dot or O squared over 2k r squared evaluated at r equals RO. That's minus q dot over 2k minus q dot over 2k. So we get minus q dot over k, which we know is less than 0. This is concave downward, which means that this is a maximum point. So therefore, we can say then that the maximum temperature occurs at r equals RO. So therefore, we can grab our temperature distribution and simply plug in R0 for R's all along the temperature distribution here. And we can simplify it too. T at RO is equal then to q dot, negative q dot, RO squared over 4k, 1 minus Ri over RO, quantity squared, plus q dot RO squared over 2k, natural log of RO divided by Ri, plus q dot Ri over 2h times RO over Ri, quantity squared minus 1, plus T infinity. So we know that the maximum temperature occurs at RO, and the one thing we haven't looked at yet is T infinity. But T infinity is the temperature of the water as it passes it next to the wall, which you know is changing. It actually goes from a temperature TMI of 20 degrees C, and it exits at a TMO of 40 degrees C. So as you can see here, as T infinity increases, T at RO also increases. So what we want to say then is that T max then occurs at the maximum T infinity, which would be TMO. So therefore we can write an equation then out for the maximum temperature inside the pipe wall, minus q dot times RO squared over 4k, 1 minus Ri over RO, quantity squared, plus q dot RO squared over 2k, natural log of RO over Ri, plus q dot Ri over 2h, RO over Ri quantity squared minus 1, plus TMO. So this is our maximum temperature here. Now there's one last thing we need to do, and that's in order to evaluate this, we need to find out what H is. So that comes into the next side of the problem. In order to calculate H, we need to first look at the Reynolds number. The Reynolds number is going to be 4 times m dot over pi times d times mu. And since we have two diameters, we're going to use the inner diameter here. If we plug in our numbers, we get 4 times 0.1 kilograms per second over pi times 0.02 meters times 855 times 10 to the minus 6 Pascal seconds. It gives us a Reynolds number of 7,450. This is going to be in the turbulent regime. But the thing we need to check then is to make sure there's no hydrodynamic entry effects. So for turbulent flow, we know that the entrance length over the inside diameter is about 10. So this means that the entrance length is going to be about 10 times 0.02 meters, or about 0.2 meters. But we already know from part A, as we go up, that the pipe length is 8.87 meters. So since 0.2 meters is much smaller than what we calculated to be 8.87 meters, then we can approximate as fully developed flow throughout the pipe. This makes things a lot easier for us. So the next thing we need to determine then is what is the appropriate Nusselt correlation. So this is table 8.4. In 8.4, we know we need a turbulent fully developed flow Nusselt correlation. A couple are provided for us. If you look here, the three that appear to be good candidates are these three right here. If we look more closely, we see that the top two require Reynolds numbers to be bigger than 10,000. However, our Reynolds number is smaller than that. It's 7,450, which means we have to go with the third one. Now, in order to calculate this Nusselt correlation, we need to have the friction factor F, which we can calculate using this equation right here, 8.21. So we'll go ahead and do that, and that'll allow us to calculate the Nusselt number. To calculate the friction factor, we say F is equal to 0.790 times the natural log of the Reynolds number minus 1.64 all to the minus 2 power. And if we plug in our numbers here, 0.790 times the natural log of 7,450 minus 1.64 all to the minus 2, we get 0.0342. This means we can calculate our Nusselt number using F over 8 times Reynolds minus 1,000 times Prandtl divided by 1 plus 12.7 F over 8 to the 1/2 power times the Prandtl to the 2/3 power minus 1. So as we plug in these numbers, we get 0.0342 over 8 and 7,450 minus 1,000 times 5.83 divided by 1 plus 12.7 times 0.0342 over 8 to 1/2 power times 5.83 to the 2/3 minus 1. Plug these numbers in and you get 56.2 for our Nusselt number. This means then our H is going to be our Nusselt number times the thermal conductivity of the water over the inside diameter of the wall, which is 56.2 times 0.613 watts per meter Kelvin divided by 0.02 meters, which gives us heat transfer coefficient is 1,720 watts per meter squared Kelvin. So finally we can plug this into our equation for Tmax. So plugging in the numbers, we get Tmax is equal to minus 10 to the 6 watts per cubic meter. This minus 0.02 meters quantity squared for 4 times 13.4 watts per meter Kelvin times 1 minus 1/2 quantity squared plus 10 to the 6 watts per cubic meters is 0.02 meters quantity squared over 2 times 13.4 watts per meter Kelvin times natural log of 2 plus 10 to the 6 watts per cubic meters times 0.01 meters divided by 2 times 1720 watts per meter squared Kelvin, all times 2 squared minus 1 plus 40 degrees C. When you plug in all the numbers, you get a value of 53.5 degrees C. So therefore, we can say that the maximum temperature is 53.5 degrees C, occurs at R equals R0 at the outlet of the pipe.